Professor George Fitzgerald Smoot, sorry for the voice, Nobel Prize winner in Physics 2006, Mr. Uwe Morawetz, founding chairman of the International Peace Foundation, and members of the team, members of the management committee, and members of the Senate, distinguished guests, ladies and gentlemen, Assalamu alaikum wa rahmatullahi wa barakatuh, and a very good afternoon. On behalf of Universiti Teknologi PETRONAS, it gives me great pleasure to welcome Professor George Fitzgerald Smoot, a well-known astrophysicist and a cosmologist to our university. He will be delivering a special lecture entitled Contemplating the Birth of the Universe, in conjunction with the Bridges Dialogues Towards a Culture of Peace. As all of us are aware, Professor Smoot was awarded the 2006 Nobel Prize in Physics for the discovery of the black body form and anisotropy of the cosmic microwave background radiation. We are indeed honored to have you, Professor Smoot, with us, and we look forward for him to share his vast experience and ideas, especially in the area of cosmology. This dialogue session is one of the benefits received by PETRONAS as a gold sponsor worth US $125,000 for Bridges Dialogues Towards a Culture of Peace program organized by the International Peace Foundation. Through this Nobel program, the foundation is bringing Nobel laureates for economics, peace, physics, chemistry, medicine, and other illustrious speakers to our country. Ladies and gentlemen, in this university, we conduct similar events such as this, which is known as the UTP Public Lecture Series. And UTP has been organizing this public lecture series since 1998, and since then has invited many prominent speakers locally and abroad. I believe sessions such as this, and also the lecture series, are valuable platforms for knowledge sharing between the speakers and the university community on various topics and issues. The invaluable experience and insights that can be obtained from these sessions complement and enhance what the students gain within the classroom and formal education. And as for the lecturers and staff, sessions such as these provide the much-needed perspective on national and global issues. It is also hoped that such sessions will encourage better understanding of ourselves, our society, and our civilization. I would not want to take away Professor Smoot's time, but I want to emphasize the relevance of his topic to us all. It is indeed incumbent upon us as human beings and as the creation of God to know our origins. And knowledge of our origins demands us to transcend traditional areas and disciplines. We have to move beyond the orthodoxy of science, physics, and mathematics. And many scientists in the modern and early modern era, as well as in the Islamic era, were also artists in their own right. Werner Heisenberg, a physicist philosopher in the 1930s, also played the piano. He was an excellent pianist who could also recite huge tracts of the Goethe. It was Heisenberg who strongly protested on narrow empiricism in science. For example, he took the view that we should stop trying to visualize what goes on inside an atom, as it is impossible to observe directly something so small. What we observe is much dependent upon our method of observation. It is similar, I assume, in studying the cosmos. The origins of the universe falls under the realm of cosmology. I would imagine that Professor Smoot would take us on a journey of the universe, its past and the future, and the Big Bang, perhaps also the Big Crunch. Cosmology goes back to the science of earlier civilization, as in the Greek, Egyptian, Hindu, Chinese, and Muslim civilizations, and not forgetting Babylon and Mesopotamia. Since then, man has thought and reflected upon the universe. In the modern age, we come across scientists like Galileo, Newton, Einstein, and Friedman, among others. And amongst modern Muslim thinkers and philosophers, such as Biazaman, Said Nursi, Said Hussein Nas, Al-Khawarizmi, Al-Farazi, and Al-Farghami are instrumental in bringing another understanding of the universe. Their success was driven by the desire to understand the universe and the general quest for new knowledge. Ladies and gentlemen, once again, I would like to thank our guest speaker, Professor George Smoot, and Mr. Morawetz, the founding chairman, and their team for being with us today. I would also like to record my appreciation to all of you for making time to be present with us today. Thank you.
Thank you, Yang Berbahagia Dato'. Ladies and gentlemen, may we now invite Mr. Uwe Morawetz, Chairman of the International Peace Foundation, to be on stage for the introduction of the second Asian event series, Bridges, Dialogues Towards a Culture of Peace.
Welcome to the second ASEAN event series, Bridges, Dialogues Towards a Culture of Peace. Bridges is facilitated by the International Peace Foundation, a non-political and non-religious foundation under the patronage of 21 Nobel Peace Prize laureates based in Vienna. The events are hosted in cooperation with various local partners, including the country's major universities, and I thank the University Teknologi PETRONAS and its rector, Dr. Zainal Abidin Haj Qasim, for hosting our event today. Since November 2008, Bridges is being continuously held in Malaysia and Thailand until April 2009, involving the participation of Nobel laureates from all fields. The second ASEAN series of Bridges is an independent contribution to the United Nations Decade for a Culture of Peace and Nonviolence, initiated by the United Nations General Assembly. It follows a series of 300 Bridges events which the International Peace Foundation has already hosted in Thailand and the Philippines since 2003. 35 Nobel laureates, as well as 13 other keynote speakers and artists, such as Dr. Hans Blix, Dame Anita Roddick, the Reverend Jesse Jackson, Vanessa May, Jesse Norman, and Dr. James Wolfenson, participated in these events. In Thailand, they were presided over by Her Majesty Queen Sirikit and Her Royal Highness Crown Princess Maha Chakri Sirinthorn, and reached an audience of 90,000 participants. As peace cannot be achieved instantly, but is a process which needs time, Bridges has not been organized as a single conference, but as an ongoing series of events in which Nobel laureates and international decision makers have built strong bridges with leaders in all parts of society and with the general public. With the basis for peace being education and synergies being the fruit of cooperation, the International Peace Foundation has not realized Bridges alone, but has carried out the program together with UNESCO and 88 other national and international institutions, including 33 major universities and schools. The multidisciplinary and pluralistic approach of Bridges in Thailand and the Philippines, and of the events now in Malaysia, reflects that peace involves all parts of society. It involves awareness and social responsibility of politicians, the business community, scientists, artists, and the media. And since peace within ourselves, our families, and our environment starts in our minds and hearts, it involves every one of us. In this sense, Bridges challenges us to cross borders and to build bridges by listening and opening up to other viewpoints, by generating new thoughts, by developing innovative forms of cooperation, and by fulfilling the desire of everyone to get to know and to learn from each other. This can lead us to a world in which we will be able to understand each other and the complexities we face today in a new light. A globalized world needs broad strategies for change to secure a sustainable future for us and the next generations. Let us be inspired by the knowledge and the wisdom that Bridges continues to offer, an opportunity to get a more inclusive, interconnected, and comprehensive view of ourselves and the world in which we live, in which we are able to create anew constantly through dialogues towards a culture of peace which need the participation of everyone. I thank Professor George Smoot, the 2006 Nobel Laureate for Physics, who has agreed to come to Malaysia to support the events. We now look forward to his keynote speech and to his important contribution to build bridges. Thank you very much.
Thank you, Mr. Uwe Morawetz. Ladies and gentlemen, before we invite our honorable speaker on stage, allow me to introduce our speaker for today. Ladies and gentlemen, Professor George Fitzgerald Smoot is the director of the Berkeley Center for Cosmological Physics, who was awarded the 2006 Nobel Prize in Physics for the discovery of the black body form and anisotropy of the cosmic microwave background radiation. He is responsible for the best picture of the early universe. Called the discovery of the century, if not of all time, by Stephen Hawking, Professor Smoot's discovery has, for the first time, given theorists hard data to use in determining the mechanism of the creation of the universe. Professor Smoot received bachelor degrees in mathematics and physics in 1966 and a PhD in physics from MIT in 1970. He has been at the University of California, Berkeley National Laboratory since 1970 and is the author of more than 200 science papers and of the popularized scientific book, Wrinkles in Time, that elucidates cosmology and the Colbert discovery. A professor of physics at the University of California at Berkeley, his honors include the NASA Medal for Exceptional Science Achievement, the Kilby Award, the Lawrence Award, and the Einstein Medal. Ladies and gentlemen, please welcome Professor George Fitzgerald Smoot.
Good afternoon, Rector Zeinen, honored guests, ladies and gentlemen. It's my great honor and pleasure to be here at the University of Technology PETRONAS and to try and get my talk organized and started. I'm going to give you the short version of the talk so that there's time for you to ask questions and we can actually have a discussion and a dialogue. And so I thought I would give you a summary of roughly where we are in our program to understand the universe from its creation up to the present day and what we might learn about the future. So what we do is we investigate the scene around us and we look at the relics of the beginning of the universe and what's happened since then, and we try and make sense out of it. And I'll explain to you some of the results we have and what we've done. Okay, so the first picture comes from the fact that we build tools, and we started building tools long ago to look at the sky. And in fact, you can trace astronomy back very, very far to the Babylonians, but also to ancient Muslim culture when Al-Mamun made the first pair of observatories, then to Galileo and to Newton and to more modern astronomers. And now we have special tools and observations that allow us to learn a lot about the universe around us. So the first picture I want to show you is from the Hubble Space Telescope. It's a deep exposure that is chosen to be sort of a blank spot in the sky. And there's no spot in the sky that's blank. That when you look out at the sky, you see a lot of interesting objects. And in this picture, if we can turn the lights down in the front, you can see it more clearly. In this picture, it's notable that what you can see are 4 stars. There's a star here, 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 and here. And everything else, the more than 2,000 objects that are in this picture, are galaxies. That is, collections of many stars. And for example, this is a galaxy very much like our own. It's a spiral galaxy, and it has something on the order of 100 billion stars in it, pretty much the same as our own galaxy. And it's spiral, very much like the galaxy we live in. And when I look at this picture, I often wonder, are there a group of people in there discussing where the universe came from, or other important sort of discussions about who they are and what's their place in the universe. You know, the same thing that we're talking about here today. And you'll notice other features in here. There are a number of galaxies. This elliptical galaxy, another one, and some other spiral galaxies that are yellow in color like our sun. Those galaxies, when you look at them carefully, turn out to be relatively near to us, and they turn out to be fairly evolved, so that most of the stars in that galaxy are burning with a yellow color, which means they're stars that are burning slowly at lower temperature. But around them, you see a lot of other galaxies that appear to be smaller. That's because some of them are smaller, and most of them are farther away, and they look smaller because they're further away, but they are white and blue in color. And that means the stars in those galaxies are burning much more brightly. So if you take an object and you start heating it up, first it glows in the red, then it glows in the yellow, then it glows in the sort of whitish light, and then it turns even more blue and indigo and violet. That's a measure of how hot the temperature of that source is, and that tells us the stars in these other galaxies are burning more brightly. And it turns out they're further away, and it takes light further to travel to them, so that we're looking at them in an earlier epoch, and that's when they're forming very bright, very massive stars that burn very rapidly and very hot. And that takes a while for that fuel to be burned up and leave behind the stars that are like our sun that take much longer to burn their fuel. And some of those galaxies will merge with each other, and when they merge, they'll end up forming spiral galaxies or elliptical galaxies, depending upon the environment they're in, roughly 50%. The one other thing I want to say about this picture, there's many things to say about this picture, but the one other thing that I would like to say about this picture is it covers a tiny, tiny fraction of the sky. The Hubble Space Telescope has a very, very small field of view. It's like a very long telephoto lens. It sees only a very tiny fraction of the sky. And if you were to take the Hubble telescope and look at every piece of the sky, if you had enough time to do that, you would see, instead of seeing 2,000 galaxies, you would see at least 100 billion galaxies out in the universe. So there are very, very many galaxies that everywhere you look and you see a star in our galaxy, which there are 100 billion of them, when you look more deeply and look behind them, you see another galaxy out in the universe. So there are a very large number of galaxies in the universe that are visible to us today. So that begins to give you the scale of what's going on in the universe. Okay. So we have a primary tool to investigate our cosmic scene, and that is the fact that the universe not only has a lot of galaxies in it, but it's very, very big. And it's so big that the time of travel for light becomes very important. So in this picture, in this sketch, the Earth is here at the center, and if we use light from the sun to make a picture of the sun, we get a picture of the sun that's 8 minutes old, because light takes 8 minutes to travel to us. So if we make an image with light that's arriving with here right now, it's really what was going on in the sun 8 minutes ago. But if I look at Jupiter, it takes 40 minutes. If I look at sort of the 50 nearest stars, it takes on average 10 years for the light to get here. If I look at a typical star in our galaxy, it takes between 1,000 years and 100,000 years for the light to get to us. Or if I look and make an image of the Andromeda Galaxy, which is the nearest big galaxy to us, it takes light more than 2 million years to get here. It's on the scale of 2 million years. So light, which we know travels very fast, the distances are so vast that it takes a very long time. If you took a picture of the Earth 2 million years ago, there would be no lights at night, there would be no Great Wall, there would be no evidence of mankind at all. We know that man didn't exist on the Earth 2 million years ago. And so you have a very different picture. You begin to look back in time. If I look out even further to more distant galaxies, I see galaxies as they were 1 billion years ago, and if I look further, a few billion years ago, and if I look as far as I possibly can, which is shown out here as a sketch of the pink and the blue, if I look out to that very great distance, I look as far as you can possibly see in the universe using light, and that's because the universe is expanding. So if you go back in time, the universe was denser, and it also was hotter, and there's a time when the universe was 1,000 times smaller than it is today, and 1,000 times hotter, and then it's nearly as hot as the sun. So when you look at the surface of the sun, you cannot see into the sun. You can only see to the surface of the sun, and then it's opaque because it scatters. It's like the clouds in a rainstorm. You can only see the surface of the clouds. You can't see inside the clouds. But with the sun, we have another trick, which is the same thing we use to study the beginning of the universe, the very beginning of the universe, and that is there are sound waves in the sun. The sun is almost a perfect sphere, but it's perturbed, and there are sound waves that travel through the sun, and those sound waves make a little pattern on the surface of standing waves, just like when you see a violin string moving or something. There are standing waves that go around the sun, and some of them go through the sun, and from studying the properties, we can actually use sound waves to give us information from inside the sun, the density, the temperature, and so forth. And that information is transmitted to patterns on the surface of the sun, and by a very careful study of the surface of the sun and the sound waves, we can then determine what the actual conditions in the sun. And that is called helioseismology, in analogy to using sound waves to determine what is the structure of the surface of the Earth. Right? You can, from the surface of the Earth, you can have seismological sensors. Those seismological sensors use sound waves that travel through the Earth that tell you about the underlying geology of the Earth, including the mantle and the molten core and so forth. So there is seismology of the Earth, there's helioseismology of the sun, and there's cosmic seismology that lets us look back past what we can see with light. So our goal in cosmology is to determine the whole history and development of the universe and understand where it came from. We can, with very careful measurements, measure back to the time when the universe was 1,000 times smaller. That's equivalent to you as a human to a time when you were 1,000 times smaller. It would be a time when you were an embryo, a very beginning embryo. And the time in the development of the universe is very close to the time in the development of humans. That would be the equivalent of 12 hours after the conception of the human being. That's when we can get an image. And then, if we look at spheres of different radiuses, we get samples of the life history of the universe, just like if I look out at the plantation, the palm plantation, and I see a field that was planted a year ago, and then one that was 2 years ago, one that was 3 years ago, and so on for 100 years, I can see the life cycle of a palm tree, right, by just looking at different samples. So we have the hope that we can make measurements in a series of concentric spheres and get samples of the universe at different ages, and therefore trace out how the universe has developed over time. So that's one of our primary programs in cosmology, is to trace out the entire history of the universe from the very beginning to the present time. And we're making a lot of progress, and I will show you that. I have been involved for most of my career in developing the technologies and the technique, the instrumentations, and the algorithms for how to make a map of the universe at its very earliest possible time, when it's just barely an embryo, just the beginning embryo. But there are people who have been making progress of mapping the universe in this sort of region, and I will show you some of that results. And we're now embarked on programs to make maps in these intermediate regions so that we can understand what's going on. We have samples, but to make really big maps where we have good statistics, that's going to take more time. So here's the idea reinforced. We live on a spiral galaxy, and we live on a spiral arm in the spiral galaxy. So we don't live in the center of the galaxy, but we live in the disk of the galaxy. But we can look out, and as we look to bigger radiuses, we see developed galaxies, spirals and elliptical galaxies. But if you look even further out, we see galaxies that are just beginning to develop as galaxies. Some of them will merge and become the more mature galaxies and so forth. But at the very beginning, they're burning brightly and fiercely and starting to form. And later on, they go to the more slowly burning stars, and they become more like the galaxies we see around nearby. Now, I can't show you 100 billion galaxies, but we can show this ring is the beginning of space and time. This is the picture that we can make, and these little things that you see on here are the sound waves, very small variations in the early universe that lets us probe back to the beginning, but lets us predict to the future. And then there's the dark ages, and then eventually galaxies and stars start forming, and they mature and form the more mature galaxies, including our own solar system. And we're one of very, very many such solar systems and galaxies in the universe. Okay. So the probe that we use is the Relic Light that comes from the beginning of the universe. It is now in the microwave region. It started out in the light region and even more intensely further back. But when it was first released, it started out as light, like sunlight. But the expansion of the universe has been a factor of 1,000 since then. And so what was visible light has now been stretched into the microwaves. Right? The wavelength has been stretched to the microwaves. So I started out developing techniques and everything, and after many years, it was developed sufficiently that we were able to win the proposal and to develop a satellite, which is the Cosmic Background Explorer satellite. And in 1992, we announced that we had found the sound waves and the ripples in the early universe, which are going to be the source of galaxies later in the universe, but also will tell us something about what the universe is made out of and how the universe itself was created at the beginning. And it was a very coarse map, and it was a very long effort, but with that discovery, we knew there was the potential. And so in 2000, we launched the next generation satellite, the Microwave Anisotropy Probe, Wmap for short. And it made better maps because it had higher resolution, because it had bigger antennas. But because we had to make sure we weren't seeing signal from our own galaxy, it gets smoothed down to an angular resolution about that. And in 2009, the launch has been delayed. We hope it will be at the end of this month. We will launch the third generation satellite, the Planck satellite, and it will have more wavelengths and much higher angular resolution and better sensitivity. And we want to make very precise maps of this very early embryo universe and get some additional information. So you see this stuff that looks like smudges, that is getting the polarization information, which will help tell us about how space and time itself were actually came into existence. So we have this series of both first ground-based and then airborne and then finally satellite-borne experiments, and there's still new generations of those being prepared. There may even be a fourth satellite depending on what we find with this satellite. And to truly understand the very beginnings, our origins, as precisely as we can. Okay, so we have come up with a model of how the universe exists that explain all our observations to date quite precisely. That is, we can do the calculations with huge computer simulations, and we are able to predict what we see to better than a 1% level. So we're beginning to be in the same regime that engineers find satisfactory, that we're able to understand things to that precision. And we have a time when the universe is so tiny and so tightly compressed and everything that quantum mechanical fluctuations are important. The universe goes through this rapid period of accelerating expansion to stretch those things that are much smaller than an atom to be very, very much larger. And then it makes a transition to a universe which is slowing down under gravity. It's not accelerating, but it's slowing down under the force of gravity. And during that time, structure forms, that is galaxies, stars, galaxies, clusters of galaxies form. And we have this cooling down when the universe becomes transparent to light, because it's like the surface of the sun. And the dark ages before the first stars form, which takes about 400 million years. And then the stars evolve and develop, and so do the galaxies merging, until in here you start getting more modern galaxies. And about here is when the solar system formed. That is when the Earth, the Sun, and the other planets are formed. And then we go on, and what we find, one new surprise that we found in the last decade, was that the universe is starting to accelerate its rate of expansion, which cuts off the formation of even larger structures that would have existed. But we are here at the present time, and we're able to look back to spheres around us, going back to nearly the beginning of time, almost 13.7 billion years. So that is our picture, and it seems a little strange, but when you put it together, it fits together extremely nicely, and when you compare it with what we observe in the universe, it describes what we observe extremely well in a statistical sense. So here is one of the nearby surveys. This is the Sloan Digital Sky Survey. Each point on here is a galaxy, and there are almost 1 million points here. So this is like the local neighborhood, just the local million galaxies out of the 100 billion. So it's less than 1/100% of all the galaxies we could possibly see, but it's a big job to catalog them. So you just take a picture like the Hubble picture, throw away the stars. For each galaxy, you have its angle in the sky, you estimate its distance, and you plot it in 3 dimensions. And as the Earth rotates, you take a series of pictures, and you get a fan across the sky. And if you then tip your telescope to a different angle, you get a different fan across the sky. So you see the fan in this sort of greenish white, and another fan behind it, which is in color. Now, it's hard to see 3 dimensions looking at a 2-dimensional sheet, so I'll show you a movie that shows you first, you'll see the structure of the survey, and then, ignoring the structure of the survey, you will see how the galaxies themselves seem to be distributed. And the problem with the survey is this limited exposure and brightness. So here it seems to be fewer galaxies. That's just because they're so far away, you can only see the very brightest ones. There are actually as many galaxies out here as there are in here. And you will see the galaxies are not uniformly distributed, but they come in large aggregations and groups. There are big places where there are no galaxies, other big places where there's large collections of galaxies. So here's the movie. So it's rotating around, and you can see places where there are no galaxies, huge voids, and places where there are many galaxies together. When there are a lot of galaxies together, we call it a cluster. When there's very many galaxies together, we call it a supercluster. And occasionally, we see even a bigger connection. So here, you see this string of galaxies. It's actually a wall of galaxies. We call this the Great Wall, right? But it's not, you know, the Great Wall in China is more like a line. We're talking about a huge sheet of galaxies that stretches across the sky. It has millions of galaxies all arranged in a big sheet. So this tells you something about it. Now, there's one other survey. The Sloan Digital Sky Survey has mostly been done by people in the United States, but with collaborators from other places. There's a European survey that's gone called the 2-degree field of view. And we're going to do a fly-through. Okay? So remember, it takes light 2 million years to get from one galaxy to the next. So we're going through very fast. But you will notice you can see some galaxies are spiral, and you can see its color. Some galaxies are elliptical. Anytime we have the knowledge, we have now a database of 1 million galaxies where we have not only their locations, but some of the properties of that galaxy. Right? Now we're going to swing out and look back at the survey. Right? It would be very nice if we could cover the whole sky, but we're only in the beginning stages, and it was a big effort to find the location of 1 million galaxies. We have to automate it. But now you can see the wedge, right? And you can see the fact that there are volumes where there are no galaxies and other volumes where there are very many galaxies. And here, this is part of the Great Wall. This is a different slice in the sky, but the Great Wall extends over a large region of space. The size of this volume, for example, is on the scale of 50 to 100 million light years. That is, light would take 50 million years to cross that void where there's no galaxies. So you see very complicated structures where there's no galaxies, and there's filaments, and there's other things that are out there. And so that's our rapid tour through the universe. But remember, this is the local universe. This is only our local neighborhood. It's like trying to judge the Earth by only driving around in Malaysia. That's the sort of the scale that we're talking about. It's actually only driving around this city to judge the whole universe. So what we do now is we do simulations to try and estimate what it is. And we have to take into account the universe is a little more complicated than we thought. We've worked for many years, that is, physicists and scientists have worked for many years to understand the matter around us. And we thought we understood it, and then we discovered there's another kind of matter. The matter we've been studying and making accelerators and so forth is no more than 20% of all the matter in the universe, of the kinds of matter in the universe. But in fact, at least 80% of the matter in the universe is something we call dark matter, which has very different properties, and we've never made it in the lab, and we've never made a direct detection of it. But we can see its impact and influence, and we're hoping in the next years, for example, in November or when the Large Hadron Collider in Geneva turns on, we'll begin to get some hints. We'll begin to be manufacturing them in our own laboratories. But if you look on the large scale, you will see the universe is very uniform, but when we zoom in, we'll see it's not at all regular. So the floor here looks pretty regular. It's not exactly regular, there's sort of random planking, but on the large scale it looks pretty uniform, and it's semi-random, but it's not that random compared to the way the universe is going to be. So now I'm going to show you 2 movies. One is the plan view of the universe, where you zoom in, you see a slice of the universe, and you zoom in from the large scale to the small scale, and you see what the universe looks like. Okay, so this is a simulation, the Millennium simulation, with 10 billion particles in it. This distance from here to here is about 5 billion light years. It would take light 5 billion years to go across that region. As you zoom in, you go from what it looks very uniform to where you see what looks like a web. And so the dark matter, which you normally cannot see because it doesn't interact with light except through gravity, is shown in white. And the ordinary matter that is shown in this color that looks like the sun, it's the thing that can actually coalesce onto the dark matter framework and produce stars and galaxies. So we're zooming in where many filaments come together in this cosmic web. So we have a large cluster of galaxies here, between 100,000 and 1 million galaxies in this region. Now we're zooming in more and more. Pretty soon we'll be able to see the distance between us and Andromeda. So now you see a small pair of galaxies here. That's like our galaxy in Andromeda in terms of scales. So we don't live in a huge cluster. We live in a very small cluster of galaxies. Our galaxy and Andromeda Galaxy are the two biggest galaxies, and there's 20 to 40 very small galaxies that are clustered around us, but we're pretty much alone. But here we're zooming back out. So here, 5 billion years. 5 billion years for light to travel across this kind of distance. On that scale, the universe looks very uniform. When you zoom in, it looks like a biological system. And it's a combination that lots of stochastic things happen, as probability accidents happen, that generate this pattern that on the average comes out correct, but individually produces interesting kind of events like galaxies and clusters of galaxies and so on. So now we're going to fly through it. It's much harder when you're inside the universe to understand it than when you're looking at it from plan view. But you can see we're flying through, and the white is the dark matter, and the yellow is the ordinary kind of matter like you see in this room that make up stars and so forth. And it is able to dissipate energy by sending out light and therefore collapse and form stars and form galaxies and also be visible to us. So you see the white making the halos. It makes the structure. It provides the gravitational potential well that the ordinary matter falls into and then produces stars. So you see that kind of a structure, and you see the galaxies coming by, and you see we're traveling at a tremendous speed. And, again, the people who made the simulation, this movie, of course, want to go and see one of the most rare and interesting objects. It's just like tourism. You go to the really strange things out in the universe. And you see where many filaments come together. And you see, in fact, that it's not static. This is a frozen time in the thing. But, in fact, these clusters will eventually merge into that cluster. It will slowly move down. Because you have to, even moving at a noticeable fraction of the speed of light, it takes millions to billions of years to move that kind of distance. Okay, so now we can do simulations to see how this came into being. So this is a simulation of what happens if a universe that only has dark matter in it. It's also a relatively small volume. The gravity has to take the initial perturbations that we see. And what I didn't tell you was those sound waves that we see at the beginning of the universe are just like the sound waves on the sun, but they're very small. The amplitude is only a part in 100,000. The universe is nearly perfectly uniform at the beginning, but it has these very small variations, and gravity has to work for billions of years to create these larger scale structures. And so what happens at the beginning is you have an almost uniform universe with these very tiny variations. But as gravity works, the places where there were fluctuations that were slightly high, galaxies will form first, and then, or places where galaxies will form first are clusters of galaxies, and then you build up this cosmic web. So let me go back and show you the movie again. You see first spots appear, and then the spots connect up, and they make like a three-dimensional spider web, but a kind of a random spider web. We call this the cosmic web. This is the framework in which the ordinary matter then is able to collect and make the stars and galaxies that we see. And mostly in the pictures you saw, you couldn't see individual stars, you could only see galaxies. Okay. So we have a simple model there where we can do the simulation. The previous simulation had both dark matter and regular matter in it, so you can see it. Now we do even more complicated simulations. They're very computationally expensive. They take thousands of processors running for weeks in order to make them. So here is one that sort of traces out the whole history. It's a wedge that goes all the way to the cosmic horizon. That is the beginning of time. The beginning of time is out here, and the present is in here. And as we look out with our telescopes, we see back, and at the beginning, we're making the elements, we're making the pieces, but the universe is very uniform, except for these tiny variations. But over time, as the universe cools down, then we go from the region where everything is a uniform soup to the point where we begin to see the first structures, and they get more and more built up and complicated. So we have this period in which dark matter dominates, and the universe is slowing down, and structure is formed and evolves. And then we have the accelerated universe start, and that freezes structure formation. That is, anything that hasn't already formed and is starting to evolve, it doesn't get a chance to, because the universe is expanding faster and faster, and gravity can't keep up, and the universe expansion gets ahead of it. So here's the same picture without all the writing on it. So you can see how, as we look back, a billion years, 8 billion years, 12 billion years, 13 billion years, we see a very different universe in these spheres that we look around us. And this is our prediction of what it should look like, and we can compare that to our observations. Looking into this region is very difficult, but we have some new techniques that we're trying to use in order to understand that region. So we're in the period of great discovery about the very beginning of the universe. The satellite that I was responsible for putting the team together and all the pieces together, the COBE satellite that made the initial discovery. This is what the map looked like when you take out a best estimate of our galaxy. If it had flipped over and looked at the Earth, you would have made a map of the Earth that looked like that, which might remind you of the maps we had of the Earth in the time of the great explorers, right? But not the way we have now. This is the best map we have of the sky. This is the Wmap map. This is the best map we have of the sky. The features are the same, except now you can see more details. There's more resolution in terms of what's going on. And this is a map of the Earth that you would have if you have the same resolution that the Planck satellite will have. And you'll see there's a huge difference between the way the Earth looks and the way the universe looks, right? So you see very clear features that are evidence of geology. You see the shape here, the shape of the Mid-Atlantic Ridge, the shape here. Clearly, there are forces that had the continents together and moved them apart and shaped them. Those forces we know are not linear forces, and therefore they couple things together and make those kinds of shapes. Where the early universe, we're able to show all the forces that were involved in the making of space-time up to this point are linear to at least a part in 10,000. So we see variations that are a part in 100,000, and you must go down to another factor of 10,000 below that before there could be any effects that are nonlinear, that second-order kinds of effects. So we're learning something about the processes of the actual creation of the space and time that tell us that it was a very simple system, very linear system, that we can try and understand very straightforwardly. So I want to sort of conclude this part of the talk and go to questions by showing you again this model of the universe, which when you first see it seems kind of strange, but when you study it and compare it to what you see in the universe, actually explains all the feature. It calls for us to have new forces and new knowledge, but it actually explains to us and allows us to calculate how the universe should behave with great precision, and is confirmed and to a high level, and tells us we have exciting times ahead of us, both in cosmology and in basic physics, to try and understand even more about the universe. So thank you, and I will stop at this point, and we can have people ask questions.
Hello, sir.
Yes, hi. What's your name?
I'm Ahmed Bashir, and I'd just like to say first that it's truly an honor to be talking to you. So welcome to UTP, first of all. I wanted to ask you a few questions. First of all, I was wondering what actually happened during the Dark Ages?
All right. Well, we call them the Dark Ages because there are no stars and no galaxies, so there is no light being emitted in the usual way of stars and you know, things like the sun. But during that time period, the framework with the dark matter already exists, and the matter is spread very uniformly because of light pressure. So the example I usually give, if I took you and put you in the sun, what would happen to you? The answer is you would get burned on the way there, but once you got to the sun, electrons would be stripped from your atoms in your body, and the light pressure from the sun itself would spread your atoms across into a big cloud in the sun. If you did that to a galaxy, it's even more spectacular what happens. So the matter is extremely uniformly spread. The ordinary matter is extremely uniformly spread in the early universe. And so it has to gather up by the gravitational forces from the dark matter particles into this cosmic web. And so during that time, they're slowly drifting, collapsing into clouds. First it was uniform, then it aggregates into clouds, and those clouds are drifted into the gravitational potential wells of this framework of matter that's kind of invisible, but is there gravitationally. And that just takes a long time to happen before you can get the first generation of stars. And it's only those really rare fluctuations that have, instead of having just the average, they're way out in the tails of the distribution curve. They begin to form the first stars and galaxies. And so in that simulation, those little peaks appeared first. So during the dark ages, the matter is cooling and expanding and being able to collapse a little. The universe is expanding, and it's the gravitational fight against the expansion and the thermal history that's going on, but it cools fairly quickly. It can form into clouds, and those clouds then can pull into the gravitational potential of what is going to be a galaxy, a dark matter halo. And then when enough clouds fall in there, you can get enough to shock and have collapse and have first generation of stars happening. So you have the hope of looking in that region because most of the clouds are made out of hydrogen, and eventually the single atoms of hydrogen combine to make H2, and there's a 21 centimeter wavelength line from that in the rest frame. So you can actually try and look for that. If you can find a radio quiet location on the Earth, you can look for that radiation from the early universe and try and map how that behaves over time. And because the universe is expanding, you can separate out the times by just what the wavelength has been shifted to. So even though it's the dark ages, it's dark invisible light at the time. It's not dark in radio and other things. There's the radiation from the beginning of the universe, and there's the radiation from the hydrogen lines, and there's a little bit of helium and so forth. So during those dark ages, it's kind of like the history we call the dark ages. During the collapse of civilization in Europe was the dark ages for science, and that's when the Muslim cultures were carrying bringing astronomy back up and building algebra and carrying that kind of stuff. But it was called the dark ages in Europe because a lot of knowledge was lost, and it was only by getting to the Muslim and Arabic and Egyptian libraries that a lot of knowledge was recovered. The dark ages in the universe, it's just dark, right? I mean, it's a little misnomer, but for a while people were sort of desolate that there might not be easy ways. But now we have come up with schemes where we're going to try and do observations of that region. But what's happening is you just need the opportunity for something that's as uniform as a glass of water to begin to coalesce so you can finally find galaxies. And that process is interesting. And we do now know that large hydrogen clouds form, and they don't stay uniform, right, and just coalesce in. They actually collapse into clouds. They separate into sort of more vacuum, fairly high vacuum, and then fairly more dense clouds. And we can see that because when the very first galaxies start up, the center of the galaxies is very bright. We call them quasars. And you can see the light from the quasars, and you can see the light absorbed by the hydrogen coming in between. There's the first line in hydrogen is called the Lyman alpha line, or one of the first lines. And you can see what's called the Lyman alpha forest. You can see this whole host of clouds that haven't yet clumped into galaxies that are between us and the very first galaxies that are turning on. And you can see later on they go away and they're just galaxies. So we're actually beginning to have some hint about what's going on during the dark ages. Right now, it's not the deep dark ages, it's just towards the end of the dark ages. And eventually the universe goes to where between us and the galaxies, the space is pretty much got a vacuum in it, and there's the little bit of matter in it that's completely ionized. That is, the electrons are stripped back off again, whereas earlier they were neutral atoms, right, in order to collapse and form stars. So we know something about what's going on in the dark ages. It's a less interesting time if you're an astronomer because it's harder to see, and I'm focusing primarily on the early universe, but I am doing some other research, which is I have a couple of postdocs and a couple of students who have hired to try and look at light from these very early stars and very early galaxies. And that light travels, and as it travels, it tries to go in a straight line, but space-time is slightly curved by the intervening matter and energy, which is mostly dark matter. And so you can try and map the location of the dark matter by looking for the fact that the light is slightly deviated, and that creates this change in the shape, the brightness and the shape, and you can hope to map the intervening material in a really straightforward way. So we can learn about the dark matter even more than what we know now and from the simulations.
Okay. So the dark matter that you're talking about is basically the black holes, the very dense material, or is it something else that doesn't emit anything else?
There was hope among astronomers that it was just gas and stars yet to be born. And then when that got to be shown not to be the case, by careful observation, one of the things you can do is look at the nearest small galaxy to us, the Large Magellanic Cloud, where you can monitor with one telescope 1 million stars night after night, and you can see if material passes in front of them, and you can then you can limit how many objects could be going between us and them, and therefore how many objects there are in our own galaxy to explain, you know, the orbital properties of the stars around the galaxies and so forth, to explain where this dark matter might be. And you can show that it isn't ordinary objects that are compact, stars that didn't quite turn on, right? They're like Jupiters, or black holes, or other things. The black holes bend the light, and you would see the effect from that. So you can tell that it's not from that. And what we're very convinced by a number of things, it's actually a completely new kind of matter. It's matter that doesn't interact with light directly. It only interacts through its gravitational potential. That it may have, there are reasons to think it might be weakly interactive. So in physics, up until now, we only know of 4 forces. The strong force that hold nuclei together, the weak force that causes the things to decay, and in between is electromagnetism, that is the interaction of light, and then the last one is gravity, which is by far the weakest force, by many orders of magnitude, the weakest force. Those are the only 4 forces we know. It turns out, if those are the ones you allow, you would like this new form of matter to only interact weakly and gravitationally, as the 2 weakest forces, and then it would have all the right properties and could explain what we're seeing, but it means there has to be a whole new family of matter that we've never seen before, never created an accelerator or detected with, you know, looking in the cosmic rays or in, you know, material that we've searched around. We haven't seen it yet, but there are reasons to suspect it might exist, and there are huge experiments that will be going on, both to look at it coming cosmically and also at accelerators, but also these experiments looking at the orbits of stars and galaxies to try and determine more about its property. So this dark matter is truly a new substance in the universe that we need in order to explain what we're seeing. And we have many evidences that this must exist. Not only the fact that the orbits around, and if you look at clusters of galaxies, you can see that there is definitely much more mass there than there is light, and even allowing that there's a lot of material in gas and in dust clouds and so forth. It's still off by at least a factor of 5, but there is a very interesting object that was discovered a couple of years ago called a bullet cluster. It's in the simulation I showed you a cluster that was very large and another cluster coming down, which I told you was coming down towards it, attracted gravitationally. This is one in which the clusters have actually gotten together and the cluster passes through. And the gases in the clusters collide because the gas is there and makes shock wave, and you can see it in the X-rays. You can see the wavefront in the X-rays, and the gas kind of stays there in the middle. And the cluster has gone through each other because galaxies are very small. That a galaxy is made mostly of stars, and it's mostly empty space. And so when 2 galaxies collide, they mostly just pass right through each other. The chances of a star hitting a star are very, very small, right? So the galaxies just go right through, right? And most of the times the galaxies don't even hit another galaxy. They just pass right through. So you see the galaxies out on this side. And then if you look at the galaxies that are behind those galaxies and see how much their light is bent, you find the bending of the light goes with where the galaxies are, not with where the gas is. And yet we know there's several times more ordinary matter in the gas than there is left in the stars, because in the cluster the gas gets stripped out and spread into the middle of the thing, and most of what's in our galaxy or other galaxies is the gas and so forth that's going to be recycled and to make the next generation of stars. Yet, we see most of the mass, right, pass through each other just the way the stars did, compact and so forth. It means that the chances of a collision is very small. Therefore, it's a very weakly interacting kind of particle, not like ordinary matter, which will scatter and interact. So we have many different arguments like that tell us this dark matter is a completely new kind of particle that has, weak interacting properties, but has a lot of energy in it, roughly 5 times as much energy or more than in ordinary matter. And that's the framework in which we were able to build the beautiful universe that we see around us.
Oh, okay. Well, I have a lot more questions, but I think that's enough for now.
Well,
Thank you very much.
Let's see if there's another candidate. I hope that more people have questions. And then
thank you very much, sir. Appreciate it.
Well, thank you for your questions.
Have a nice time in Malaysia.
Hi. Good afternoon. Sir, as you know, the 100 billion galaxies are present here, and it's all visible today and are arranged in non-uniform distribution. In this aspect, how we evaluate or measurement the radiation pattern of light among such galaxies at different environment condition in the universe?
Okay. I'm sorry, I missed part. You were talking about the hundreds of billions of galaxies
yeah,
and the radiation pattern of light from them.
Among the galaxies in universe.
Yeah, I'm still missing part of the question.
The radiation pattern, because these are visible and that are radiating the energy or light among the all. That's why what will be the radiation pattern between the galaxies?
Okay. So most of the light in the universe is the light from the very beginning of the universe. This thing that I have been using during my career to make an image of the embryo universe. Most of the light that exists in the universe, the whole universe is filled with a sea of light, and it's expanding and stretching the light out, but the light is still there. It is most of the energy and most of the light is in that radiation. Roughly about 1% more light is light from stars, right? So when the stars start burning, they start doing nuclear reactions, and for every time they do a nuclear reaction, they generally send out one photon that goes out into the universe and adds to the general light in the universe. And as part of the Cosmic Background Explorer satellite, the COBE satellite, we had an experiment to look for this light where you can look out from the galaxy out past the other galaxies and just sum up the total light coming from the early universe. And we found that there was roughly 1% more energy in the universe than in the radiation coming from the very distant universe, that is the first generation of stars and galaxies. And, the fact that we live in a galaxy means that in the galaxy itself, there's a lot more starlight. There's a lot greater density of starlight. But when you get away from our galaxy, it gets less. And so if you ask, in our galaxy, there's almost as much light and starlight as there is from the early universe. But between galaxies, it's a big factor, but almost a factor of 100 difference. There are other things that are out there, other kinds of light from particles colliding and from other things happening. But generally, more than 90% of the light and the energy that's out there is in the cosmic background radiation, the relic radiation. The rest of it comes from the galaxies. So the galaxies, even though there are very many of them, do not fill up all the volume of space, and they don't really produce a huge amount of energy, except when when you're living near the sun, you think the sun is very impressive, and it is, right? But when you compare that to how hot the beginning of the universe was, the entire universe glowed like the sun everywhere, whereas now it's only very small pieces of the universe that glow like the sun.
Okay. Another question is, what parameters you have on which you are going to develop a map for such galaxies?
Right. So the interesting thing was that the first thing you think when you see the map of the embryo universe is those small variations are the gravitational seeds to make galaxies, and you can predict what the galaxies should look like. Unfortunately, you're seeing only that at a radius that's roughly 14 billion light years away from you. And because of time constraints, unless you're willing to have a grad student who will work for 14 billion years, right, and make observations 14 billion years later, you won't see what the universe looks like now until 14 billion years more. And so you have to infer it by looking at intermediate steps. So you don't have a direct map that goes to the other map, although you can statistically estimate what it would be. But if you're willing to wait longer, you will see the galaxies from those original seeds show up. You'll see them as early galaxies and then as later galaxies. The longer you watch, the more you will see, except for the fact that the universe is accelerating expansion. Some of those will go out of sight because space will be growing so fast, light can't get to us from them. So there'll be an issue there. But if things were reasonable, if you waited long enough, you would see galaxies form and see that structure confirmed. Here, we have to do it statistically. Just like I said, you see the 1-year-old trees and the 2-year-old trees, and you see the pattern, and you see your model of how a tree grows, and they match, right? And you can see how it goes. So we do have predictions, but we don't have the patience to wait the billions of years to see right now. Maybe later we will have.
Okay, sir. Thank you, sir.
Thank you.
Ladies and gentlemen, due to time constraint, we may only allow 3 more questions. Appreciate if one person can just forward 1 question. Thank you.
So we'll do this one over here, and then we'll go back to you.
Hi, Professor George. I would like to ask a bit about Big Bang Theory. And you have once said that your research team is keen on understanding the Big Bang in order to predict the future of the universe. And Stephen Hawking once claimed that if the rate of expansion 1 second after the Big Bang had been smaller or slightly higher, we won't have the universe that we have now today. So my question is that the Big Bang happened by chance, or the Big Bang follows some mathematical equation? And another question is that if the universe did apply some mathematical equations, if the Big Bang were to occur again in the future, will we get the same universe as what we have today? Yes, thanks.
All right. So this is a question. This is a mixture of philosophical and scientific questions. And so the interesting thing about the universe we're in now is a lot of what shows up is by chance, but the overall structure of the universe is actually fairly well determined. It's like when you ask 2 voters how they're going to vote, you can get a very wildly answering. But when you ask 1 million voters, you get a very good statistical thing. So we have 100 billion galaxies, so we have pretty good statistics on how galaxies form and so forth. We haven't studied them all, but we're beginning to study them. And so the question is, how repeatable is that? And the answer is, there are some things that automatically adjust in the universe so that the expansion rate and things will take care of themselves. It's the very beginning, when you're first forming the structure of space-time, that it matters. And then once you have that, the universe will adjust itself, and the formation of galaxies may happen a little earlier or a little later. But what becomes critical is that you make it through that early period, so you can create enough space-time that you have a big enough universe to have a good sample. But we can only see a limited part of the universe. We have reason to expect that the universe is much, much bigger than the 14 billion light years we can see in every direction. It could be very many orders of magnitude greater than that. So when I say there's at least 100 billion galaxies, that's ones we could see. There could be many orders of magnitude greater than that. There could be 10 to the 5th or 10 to the 10th times more galaxies out there. And then you'd have a good statistical sample if you waited long enough to sample that. So I invented this term, which we call cosmic variance, which really is short for cosmic sample variance. We're limited to see only a certain volume of the universe because that's all the further light can travel in the story of the universe. But it's still a pretty big sample, and the fluctuations aren't that large, except in the things there are only very few of. So when people are zooming in on that one particular huge cluster of galaxies, you don't have billions of galaxies. You may only have 1,000 of structures like that, and therefore you begin to have less of a sample and less certainty in it. But now one of the questions is, if you go back to the very beginning of the universe, if you have fluctuations in the parameters, does that actually change some of the fundamental parameters of physics, or does it just make the random variation a little different? And if I look on a big enough scale, I'll get the same average answer. And that's something we don't know the answer to. We speculate on it, but we don't have enough observations and enough constraints on our theories to tell us, if you made the universe over and over again, which is one possibility in some models, you make many samples of the universe what we call the universe, but there are many, it's only a portion of a much bigger universe where there are many different samples. If the laws of physics might vary, and some of them are very hospitable to life and some are not so hospitable to life, because some are going to make a lot of stars which are stable and last a long time, and some won't make stars, right? And so we don't know what the case is. We're not surprised we find ourselves in a universe that has a place that's stable and conducive to life, if that was a variation. But it's a very tricky thing to do because you're doing posterior probability on something that's an infinite sample. One of the things that can easily be is the universe is infinite, and there are infinite many tries at making universes, and therefore doing your statistics properly is a really tricky business because you only know the answer, you don't know the premises to begin with. So it's an interesting problem, but we're not quite equipped to solve that kind of a question yet. So, yes?
My name is Wan Ahmad Faisal, a final year student in chemical engineering. I've gone through your book, Wrinkles in Time, last week in the bookstore, and also watched your videos in the TED Talks. And since I have prepared a few questions, since the MC doesn't allow me to go further, but I will ask you one final question. In modern or this so-called postmodern era, one of the great crises is the poverty of metaphysics. Would you agree that for modern science to remain relevant, especially your own field, astrophysics, we need to integrate the element of metaphysical science into the scientific research? That's my questions.
All right. Well, we could debate and argue about this. I don't think that science has a poverty in the sense that there's tremendous richness of possibilities in science and a tremendous number of new things to be discovered and understood. But science is not all there is to the world. You still have to decide what you're going to do with your knowledge and your innovations, what products you're going to actually make and that people will buy and use. And we have a kind of a market system that makes those kinds of decisions. But you also want people to understand science and have a perspective so that they can then use other judgments, moral and ethical judgments, to decide what are really good things to do. And so I wouldn't say that science itself is in poverty. I would say science is not a complete decider of what everything should be. But right now, we need science in order to keep our economies going strongly. We need science to solve certain global problems like climate and energy that are coming up. And we need science to improve the medical care and health of people to make it so we can make it so that people can have long life expectancy and good health so that they can do their good work and also enjoy their lives very much. So it's not that science is everything, but that science has tremendous benefits to bring to society, and we have to be able to pursue the science and find out what we can to really take advantage of it.
Good afternoon, sir. My name is Dhanaraj, second year, first time chemical engineering. I just wanted to know, want to know what is beyond the universe. I'm very curious on that. What do you think is beyond the universe?
Okay, so there's a simple answer and then a little more complicated answer to the question. So imagine the very simple situation. The Earth you think is roughly a sphere. Now imagine it's idealized as a perfect sphere. Every point on the Earth, on the surface of the Earth, is equivalent. So I'm suppressing one dimension and only letting you live in two dimensions. Is there any special point in that sphere? The answer is no, because I said every point was equivalent. So now we have a north and south pole because the Earth is rotating and we have a coordinate grid. But you could, if the Earth was not rotating, you could swivel the Earth around and it's completely rotationally invariant. Every point would be equivalent. And there's also no edge, no beyond, it's bounded, it's finite and bounded. You can also imagine a universe that's infinite. So think of a plain sheet that goes to infinity in all directions. And infinity means not to an edge, but forever. No, you keep going and you keep going and you keep going. So there's a simple geometrical topological answer. You can either have a closed space that has no boundary, right? So there's no boundary condition. You can make spaces like a sphere or like a cylinder or something where there's no edges. This goes to infinity in one direction, it's finite in the other direction. Or an infinite plane, right? You can make very easily and understand in two-dimensional objects in three-dimensional space because our brains are designed for three-dimensional space. You can understand such objects that have no boundaries and either go forever or are finite. And so then the question is, well, what's before the beginning of time or what's outside the universe? There isn't anything on those kind of situations. But there's another possible solution, which is there is a beginning of time, but outside the universe is even a more spectacular universe that's accelerating its expansion all the time. And so almost the entire full universe is taken up in an accelerating part, but every now and then a little tiny piece has a quantum fluctuation that breaks it off, and then it goes into the decelerating mode, and we get something simple like the universe we see, which is very much larger than what we can see, but makes the galaxies and so forth. And that's just like, you know, sesame seeds on a giant roll that goes forever, right? So that most of the universe is the sesame seeds, is the roll, and only a tiny fraction are sesame seeds, and yet that sesame seeds holds hundreds of billions or more galaxies easily, right? So the scale that you can have is so forth. So your answer about what's outside has to do with what the universe is really like, and also what your definition of the geometry and topology of the universe is. And there can be very simple universes that just exist and are finite, and there can be very complicated universes that are not only go forever in all directions, but have very complicated topologies. And we don't know for sure, but we know the universe we're in came in such a way, it created a very simple topology for the part that we can see. We know that it's very big and it's growing, right? That we can understand. So we have one last question. Oh, we have two last questions, huh?
Good afternoon. My name is Muhammad Biasa Azari, Foundation, first semester. I would like to ask about annihilation process or total destruction involving antimatter. And please give some phenomena involving this process. And could you explain the prospect to use in annihilation process for the source of energy of the future?
All right. So for those of you who don't know, one of the things that's very necessary in the universe and is shown to exist in the universe, it's necessary for cause and effect to be valid. And being scientists and engineers, we like for there to be a rational, so forth. We think cause and effect is very important. But the fact is, it's verified. For every particle there's an antiparticle, which has exactly the properties of that particle, but with the properties so that when you add them together, you get pure energy. And that allows, when that happens, that allows for cause and effect to be valid no matter what frame you're in. And so we understand for lots of reasons that in the very early universe, we had a kind of a chemical equilibrium, but it's a chemical equilibrium in the hydrogen physics, not in chemistry. But you have chemical equilibrium in nuclear physics and high energy physics in the weak interaction, everything else. And when you get to sufficiently high energies, you will produce equal, the energy gets spread equally in every possible state. And some of the possible states are antimatter and matter pairs, right? So we know that in the very early universe, there is essentially equal amounts of matter and antimatter. And one of the problems we have is that means there should be equal amounts of matter and antimatter in the present universe unless some process came and gave us a slight excess in the early universe so that we could be made of matter. So one of the early sets of experiments that I did as a new PhD was to search for this antimatter. And we were in our experiments able to show that in the particles that come to us from around the galaxy, that less than 1 in 10,000 of those could be made of antimatter. We didn't see any positive evidence for antimatter, but we searched through 30 to 40,000 particles and tested to whether it was antimatter or not, and none were, as far as we could tell, antimatter. And at that point, I said, okay, that means there's no antimatter stars or anything. I should go into working on something else. But what that means is antimatter certainly exists, but it doesn't necessarily exist on large scale, so that it's in planets or stars or so forth. So the other way you can tell, you can look at clusters of galaxies, and if one galaxy is made of antimatter and the other one's not, which is what you would infer from the fact there's none in our galaxy on a significant scale, then you would say when an anti-galaxy came near a matter galaxy, that the gases, when they collide, would annihilate, and you would see this huge eruption of energy and gamma rays coming to us. And you don't see evidence of that. So you can kind of guess the matter is separating even more than that. So if you want to solve the energy problem by finding a big mine of antimatter, that seems unlikely. If you want to make a really good battery by making a bunch of antimatter and storing it in a magnetic container and letting a little leak out to annihilate with matter, it's a very effective battery because you get 100% conversion of matter to energy when you do the annihilation. So that's why in the Star Trek they have the matter-antimatter pods. It's the most efficient way, you know, for the writers to give them energy to fly around the galaxy. So it is possible on the Earth to make antimatter. It's a little more difficult to store it safely, and but it's not, you know, it's not likely to be a solution to the energy problem right now, unless we learn how that there are extra dimensions and we can tunnel and take shortcuts to places where there's a lot of antimatter and bring it back, and just, you know, careful engineering control, right? It's sort of like some people are worried about nuclear power, but it's very relatively safe. People are more worried maybe about fusion power, thinking the sun is close enough. But as you go to more efficient energy sources, you have to be more safely engineered. But it's certainly a possibility that that might happen someday. It isn't going to happen right away in time to solve the oil shortage, right? It's a little longer away than that, unless something really spectacular happens very soon. Right? Yes.
Hello, sir. Very good afternoon. I'm Rizwan Mumtaz, postgraduate student in electrical engineering. My question was just related to the experimentation methods that you usually basically carried out in astronomy or so. Like you also mentioned in your talk that it takes almost billions of years for the light to travel all the way from the space and to reach the Earth. So my question is just the information that we extract from the light or the images that we take of the galaxies and the many objects in the universe, isn't it a bit too old? I mean, how can we accurately predict the nature of the universe that exists today? Or maybe we speculate the nature of the universe that will exist in future. I mean, how does the credibility of this information comes from? Do you take any extra features or the factors into consideration of today's world before predicting something about the today's nature of the universe based on that previous knowledge or the information that is very old?
Okay, so there's many parts to the question, and I'll answer it fairly simply. The thing that's difficult to get used to is that on a human scale, the universe doesn't change very much. So for a long time, people thought the universe was static because on the entire history of the human race, the stars hadn't changed very much, and they hadn't understood that anything could be changing. And so even though it takes light 2 million years to get here from Andromeda, it actually takes, on the scale of 100 million years, for the sun to orbit around our own galaxy. Right? So the time scales that go on in the universe are extremely long. And so if I wanted to know what's happened in the last few minutes, my sample of the universe is no further away than a radius to the sun, right? But if I'm willing to average over millions of years, right, tens or hundreds of millions of years, then I have a sample that has a fairly large amount. And so now it becomes a question of quantitative. And then you might ask, well, what has happened in the intervening time that may have affected the light that's traveling here from a great distance? And the answer is, to first order, that light is unaffected. The only thing that affects it is its wavelength gets stretched by the expansion of the universe. That's because the universe is nearly perfectly uniform. That is, it's nearly as perfect as a perfect sphere of marble or a billiard ball for parlor games. It's extraordinarily uniform, and so the expansion is very uniform, and it stretches the wavelengths extremely uniformly. It's only when you get to the part in 100,000 you start seeing small variations. Most of those you see in the early universe, and now more than a factor of 10 down below that, you see the effect of intervening clusters of galaxies and the gravitational bending. That's a very small effect, but the fact is we're now trying to go with the third generation satellite to measure things so precisely we can begin to see those second order and third order effects in order to learn about the intervening history of the universe. So we want to see the light coming from the beginning of the universe, passing through the matter, by the matter in the dark ages, and so forth. And the primary effect is gravitational bending of the light, not absorption or so forth. It's very rare that the light gets absorbed or scattered. It only happens on a significant scale when you go through a very rich cluster of galaxies with a lot of hot gas in it. Then you might get as much as 1% of the photons being scattered, but they only get scattered. They don't get absorbed or whatever. They get scattered to different angles. And so you get another view of the sky. You get a chance to sample what the universe looks like, you know, with light coming in around that cluster of galaxies and some of them getting scattered to you. You can check to see what things going on. So we worry very much about that. We worry about it because it might affect what we're learning about the early universe, but we also worry about it because it's a way we can learn something about what's happening in the in-between times. And so we study that and we think about that very much. And in some ways, the universe has been very kind to us that those effects are very small, but that they're just big enough that we may now be able to use them as a tool. As we get more and more precise, we may be able to use the second order effects. It's like you're doing, you know, seismic scattering, and there's an earthquake that appears very far away, and there's double scattering, and you can finally see some local structure once you really interpret your data carefully. It's a very much more tricky and requires tremendously careful thinking and very powerful computer analysis, but we're beginning to do that. And you design special experiments to test it. You know, we're designing big telescopes on the ground to look at clusters of galaxies just to look for these kinds of effects. So your question is good, and the answer is nature. The universe has been very kind to us that it mostly doesn't bother us, so we can make the discoveries and make the first interpretation. We can tell what the universe is made out of. By looking at these sound waves, we can probe the beginning of the universe. We can tell what the universe should be going forward. But we know from just seeing these sound waves on the surface, we can tell a lot about the geometry of the universe. We can tell that it's made of dark matter, dark energy, and ordinary matter at the percentages that we have other indications of. But we can now use the second order effects to try and learn about what's happened to the matter in intermediate times. So we're just very lucky that things work out so well. So thank you all. Am I taking another question, or are we closing it?
We are running late of time now.
So would you like to answer one question?
Oh, okay,
Okay. My name is Rajesh Azad. I'm a postgrad student in Mechanical Engineering Department. Actually, I wanted to ask a few questions, but I'm allowed only to ask one. Would you elaborate your the thing you said about your discovery that it's like seeing God? So can you please elaborate? Thank you.
Okay. So what at the time at the time the discovery was made, we knew very limited amount about the universe as a whole, and this discovery let us understand the two measurements: the measurement that this was radiation from the beginning of the universe, and the discovery we could see the sound waves from the beginning of the universe. Meant we knew we were on the right track. We had the sort of, it's like first being able to see DNA, right? You have an idea there's this double helix, but you don't know what's on the double helix. Now we're going back and mapping the genome, the genome for the universe as opposed to it. So in some sense, we're seeing the program or the plan for the creation of the universe and the development of the universe being laid out in front of us. So it is really, it's like seeing the handwriting of God telling you how He intended the universe to be created. And so to me, I knew it was very profound because it meant, yes, the Big Bang is correct. Yes, we can see structures. With these structures, we will have the tools to understand how the universe developed and understand what it's made out of and how it's going to develop over time. And so far, in the intervening 15 years since that discovery, well, it's more than 15 years now, 16 years, we have started to fulfill that promise. We've got much higher resolution maps. We've got better simulations. We've got good understanding of what the universe is made out of. We understand the geometry of the universe. And we have multiple ways of seeing that and understanding and checking that what we're seeing. So it turned out, it felt that way, and it turned out to be that way, that it really sort of is given the key to reading the secrets of the universe.
Thank you, Professor, for sharing with us your experience and insights. It has been a beneficial session for all of us. Now we'd like to invite Yang Berbahagia Dato Dr. Zainal Abidin Haji Kasim onto the stage to present a token of appreciation to Professor Smoot. Thank you Yang Berbahagia Dato and Professor Smoot. On that note, we have come to the end of today's program. We hope that everyone has benefited from this session. Ladies and gentlemen, please rise for the National Anthem.